Okay, thank you, Ronnie. Thank you for the organizers for this conference. I will talk about the work we have been doing in collaboration with the Buletich group in MIT, the experimental part, and also with Gernot and Vasily from Berlin, TU Berlin. And let's start defining the rules. I will try to compare classical and quantum heat machines. What do I mean with classical and quantum? So if I have a trap system, classically defined by classical laws, I will compare it with exactly the same system, trap, but now governed by quantum laws. And we know that this system behaves very differently. Classically, you can have a continuous spectrum. Quantum, you have energy quantization. Classically, if the system is at a thermal equilibrium at 0 temperature, the energy of the system is 0. Quantum, you have 0-point energy. Phase space distribution versus Wigner distribution, uncertainty principle, etc. So my goal during this talk will be to compare the same heat machines, but the working fluid is ruled by classical laws, by classical mechanics. The second is ruled by quantum mechanics. And what do I mean with identical? It's the same working fluid, same potentials, same baths, same temperatures, etc. The only difference is how you describe your working fluid. And the question is which one is better or if they are different. So I will focus on the Otto cycle, that the Otto cycle is the ideal representation of how your car engine works. And basically, well, some people already mentioned, but classically, you have a gas that is compressed in an isentropic way. Then you heat your gas, then you expand it isentropic, and then you cool it down, and you have two volumes defined. And basically, the efficiency work extraction requires that the rate between this volume and this volume to be more than 1. So you need to be able to compress your gas. If your gas is an incompressible fluid, you will not be able to extract work, for example. And the efficiency is defined by this. The real efficiency of the engine is defined by this equation, which is always bounded by the Carnot. This is just the rate of the heat capacities. So if one plots this efficiency as function of the compression ratio, this is the efficiency. You can define 3 areas. One where your machine will work as an engine. The second, where it will work as a classical refrigerator. And here you are working as a heater. So basically, again, as shows, if your working fluid will be incompressible, you will not be able to extract work. And in reality, you cannot, in principle, the Otto cycle could reach the Carnot bound just at this point, where the compression rate is equal to this ratio between temperatures. But in reality, you have some critical compression ratio where your engine will explode if you pass this critical. So in general, you don't pass some threshold. So it will be nice to try to do Otto cycles that are highly efficient with low compression ratio. So this is completely classical. Let's go to the quantum and what will be my Otto cycle. I will have 2 potentials, random potentials, 1 dimension. Here in this axis, I have just the entropy. So I will do something similar to the classical Otto. I start at point 1. I deform in a very slowly my potential. So the quantum adiabatic theorem holds. Get to 2, connect to a hot bath, get to point 3, then deform back the potential to 4, and then finally I cool down with a cold bath. And work will be just defined as work is just the difference of the expected values of the Hamiltonian of the system in the different points. And I will use the convention in that negative work is a heat engine. So as I told you, one important assumption is that you want to do these transformations, or the standard mainstream assumption idea is that you should do this as slow as possible to avoid entropy production. I will go in the second part of my talk to this stage. But let's now define, there are two types. When you deform your potential, you can separate your deformations into two types. One that I will call simple, where it's well known because most of the works in the Otto cycle work in this simple deformation, and I will define it in the next slide. What is very interesting is that if your working fluid is governed by classical laws or quantum laws, the efficiency in this deformation is the same. The operation mode, if your engine will work if your machine will work as an engine or as refrigerator, is the same. Work could be different between the classical and the quantum. And there is the other type of deformation, what I call the not so simple deformation, where it's mostly unknown. There are very few papers who consider this deformation. Efficiencies will be different. Actual efficiencies, different operation modes, and different work. So what are these deformations? So you have a potential. This defines you some energy levels, and your second potential, and you have also the energy level. So the simple deformation will be that deformations where all the energy levels between the two potentials are just scaled by a constant. So imagine you have an harmonic oscillator, you open it, or you close it, all the energy levels are being multiplied by the same number. Also, a particle in a box is the same. So this is what I call a simple deformation. And I will focus on the not so simple is where the cases that they don't follow this rule. So let me show you an example of a classical machine that doesn't do anything. Imagine you have a particle or you have a gas trapped in a box. The energy, if the gas is in thermal equilibrium, is just proportional to the temperature. And now if we put a barrier which are the area of the barrier, it will be equal to 1, we will have the energy will change, but the energy decays exponentially with the height of the barrier. So in principle, if this barrier will be a delta function, there is no difference in energy between these two cases. But let's see what happened in the quantum case. In the quantum case, we have energy levels. And some of these energy levels at the center where I will put my barrier are 0, but some of the wave function, but some of them are not 0. So when I put now some barrier, some delta function on the center, the levels which are not 0 will be push up, will move depending of some, could be up or down, while the others which are 0 will not feel the presence of these barriers, so will not move. In this simple way, we are doing this not so simple deformation of the Hamiltonian, and the next step is now to build with this heat engine. So I will consider the following cycle. My two potentials are just a particle in a box without barrier and with a delta barrier. I will assume that the temperature of the cold bath is 0. This G prefactor will be important later, so remember it. And let's compare classical and quantum. So classical, by putting the barrier, I'm not changing the energy, but quantum, by moving this level, I'm changing the energy. And if I do, so this was A to B, if I see the other points, again, classically, I don't change the energy, but quantum, I'm changing the energies. And if one calculates the work in these two cases, well, this one, you don't have any change of energy, the work will be 0. In this case, you are extracting work. And if we now generalize a little bit this example and let this box to open and go and to close it to compare to the Otto, so here again we have the classical one. We see that if G is positive, here in the area that you didn't expect, classically you didn't expect to work your engine. You have efficiency, higher efficiency. G negative also, you see it works different. It's less efficiency, but then where you expected a classical refrigerator, you are extracting work. And what is interesting is that here at 1, where you are not doing any compression of your engine, quantum mechanically you are extracting work. So in principle, quantum mechanically you can do a heat engine with an incompressible fluid, while classically you cannot do it because you need to be able to compress. Also, if you have enough control on your system and you can optimize G for any value of the compression ratio, you can be at the Carnot efficiency for any compression ratio. So quantum mechanically we can do things that classically we will not be able. So now I will go to, yes?
But it's probably not quantum versus classical, just you inserting delta function, you classically never adiabatic. If you give some weights, then classically it will be the same. And this problem, is it large and it's obvious that there is no difference between quantum and classical. Your argument is not referring to ground state.
Sorry, again?
So in this sense, I just don't see difference.
Could you repeat?
I'm just saying in your argument, quantum is actually when n is equal to 1 or maybe 2. When n is equal to 10, it's already classical. So I think in your limit, you just consider very specific.
And you mean the number of particles, or you mean the levels? Okay. No, with one.
If you consider finite widths of your barrier, then quantum mechanically and classically will recover the same result. So you just made very general statement.
First, okay, this is one example in one potential. You can do in other potentials, and you will, like harmonic oscillators, etc. You also will see difference. Like if you treat the harmonic oscillator classically or quantum, you will see difference.
Okay.
Okay.
Say you consider adiabatic and non-adiabatic, not quantum and classical.
Okay. So maybe related to this point is the thing about these transformations. Up to now, we in general want to do it very, very, very slow, these transformations, because we don't want to change the entropy. And we know that if the transformation is very slow, populations will not change using the quantum adiabatic theorem. And in this way, we are sure that the entropy is not changing during these transformations, and the energy difference is work. So what's the reason of this is that if we start in a thermal state, and by doing our transformation that doesn't change the populations, if the transformation is simple, the one that you have these relations between the energy levels, basically, you can rewrite these populations as a thermal state of the hot bath. It's a thermal state where here I have the energy levels of the hot bath. So at the end, you end in a thermal state of the final potential. It's important that this is a thermal of the final potential, not only of the initial potential. And we know that a thermal state has, for a fixed entropy, it's the state with minimum energy. So basically, if we will do a fast transformation where we will not end with the same population, because of this property, we will increase the energy, and this, in turn, will reduce the work extraction and efficiency. But what happens if the transformation is not simple? Again, if the transformation is slow, we don't change the populations, but now we are no longer in a thermal state of the final potential, because we cannot rewrite our initial populations in these ways, because this inequality is no longer true. But we are what is called in a passive state that it was mentioned already a couple of times during these talks. And very quickly, what is a passive state? So a thermal state is a diagonal state in the energy eigenbasis, where the populations reduce as function of the energy, but reduce in a very particular way, exponential with the energy. But a passive state is like a generalization, let's say, where also you have a diagonal in the energy, populations go down, but they don't have to go down in the same way as for the thermal state. One property of the passive state is that also for fixed entropy, minimize the energy. So if we will do a fast transformation, we will change populations, we will reduce the energy, and work extraction and efficiency will be reduced. But what is interesting, considering a passive and thermal state, is when you consider several copies of the same state. So thermally, if I have one system in a thermal state, two copies of the system in the thermal state will be thermal, 3 copies will be thermal, etc. Multiple copies will be thermal, all of them are thermal. So, again, fixed entropy, minimum energy, best transformation, do it as slow as possible, do it slower. But if you are in a passive state, and here is the difference, there are situations where if you can be in a single system, the state could be passive, but when you take 2 copies of the same system, the state is no longer passive, and you have some energy in principle that could be extracted by exchanging these populations. Basically, this effect is because maybe in your single copy of your system you don't have level crossing, but when you take 2 copies you have a level crossing. So if we end in this state, the final state will be what is called non-passive, and in principle this doesn't minimize the energy for a fixed entropy, and we can ask what is the best transformation. So again, if the transformation will be slow, we don't change populations, we end in this non-passive state, and there is some energy we are not extracting. But if we do it fast in a smart way, in a way that we exchange at the end of our transformation, we exchange these populations. Again, this transformation is isentropic. I'm not changing the entropy. So all the energy exchanges work. If I can get to this final passive state by not doing quantum adiabatically the transformation, I can reduce the energy and increase the work extraction. Just one comment. One interesting thing is that for a discrete spectrum, you can have 1 copy to be passive, 2 copies passive, and 3 copies could be non-passive, for example. But if you have a continuous spectrum, and the 1 copy is passive, the second copy is passive, 3 or more has to be passive. So there are differences between the properties of passive states and multiple passive and non-passive states if your spectrum is discrete or is continuous. So let's exploit this in a particular example. Assume you have a 3-level system, and we will do a very simple deformation. We will just move the middle level. So this deformation is what I call not so simple. So then the state is passive. So let's do the same now with 2. Again, I'm just moving one of the levels. Second and ground is not being moved. Then the state is non-passive. So now I want to compare, to do this modulation at different speeds. So it's exactly the same modulation, and the factor lambda somehow controls my speed. So I start in the same point, end in the same point, but I do it very slowly for the red curve, faster for the blue, and very, very fast for the green one. And besides, I will add in part of the process other modulation that allows population to be transferred from one side to the other, from one level to the other, because in this way I can convert this not passive step into a passive one. So if I do a slow modulation or an ultra-fast modulation, in the slow case, I'm in the quantum adiabatic theorem, so populations do not change. In the very, very fast, I'm in the sudden approximations. Populations also do not change. I end in the non-passive state. But if I do it in an intermediate regime, I can make this exchange of populations and end in this state. And just to show you some results for the work, as function of how long is your stroke, how long is this transformation, again, this is the sudden approximation. If you do it very fast, your system doesn't even notice that you are changing, and you don't change populations. Here we are in the quantum adiabatic regime. And we see for some parameters, I choose that in the adiabatic you don't have work extraction, but then when you start making faster and faster, you start extracting work, and when you do it very, very fast, you go back to the sudden approximation, and you don't extract work. So in this kind of scenarios, maybe it's better to do faster your transformation than slowly, and at this point you have a perfect population transfer, and it's the best you can do. And if one now looks the efficiency instead of the power, again, in this case, I choose one that you have 0. You have a boost on the efficiency because of this effect of transferring the population. So if the it's not always the best to do it very slowly, your transformation. So just to summarize, I talk about the Otto cycle, and I say that it's very important to consider this division, that it's built, it depends or defined by your transformation. There's the simple one, and there's this not so simple, that is basically just that your energy levels do not scale in an homogeneous way. And in this regime, one can find interesting things, like even efficiency with compression ratio equal to 1, heat engines with compression 1, or even to be able to do it fast, your cycle, and get more work extraction. And with this, I conclude, and if someone has questions.
So it seems like your definition of a quantum machine basically really mostly involves the quantization of energy levels.
Yes, at this point is
something like that can also happen with waves and so on. So I was wondering, are there any kind of concepts for, I don't know, light or kind of things where such things could be tested? Like it seems that you don't need a complex quantum system for testing these kind of concepts.
sure, but you know, the idea is I have a heat machine. I have the classical and the quantum exactly the same. I want to try to understand just the fact that quantization, if this will make better or different. You can maybe mimic this quantum heat machine by a classical system, but this will be other things. So if you have this option, classical and quantum, which one will you choose, and if this gives you some different behavior?
It wasn't even meant as a critique, just
okay.
Like you could maybe you could build a heat engine which works just in a very different concept. It doesn't have to be quantum.
Okay.
Hard, there are very hard restrictions of what some people might call a quantum system. And I think a lot of them you might not even need, and you could build a quantum, like a heat engine, which would outperform traditionally known heat engines there. That's why I'm asking that. It's kind of an interesting thing.
Okay.
Some of the phasing though, right? And also the phasing of classical waves.
Yeah.
This you can say. So do you call Anderson localization light quantum or classical? It's a different discussion.
So, if there are no further questions now, I think there is.
Nice point that you're making here at the end. If I start a two-level system off and send in a pulse, turn it on and turn it off adiabatically, that's bad news for me because I want something to stay in the excited state. And what we find is that if I have just a tiny bit of quantum coherence to begin with,
Okay.
I can turn things on adiabatically, off adiabatically, and get a lot of probability staying in the excited state. That might help you here.
Okay. Thank you.
So I think we'll need to get here at 2 o'clock. And there are a few lunch places around here. You can ask me or